Welcome back, dear all, in our next session on displacement, velocity, acceleration, and jerk of the follower in a cam mechanism which is moving with uniform acceleration and retardation motion, simply called as UARM. So whenever you have a question in front of you while solving a question on uniform acceleration and retardation motion, you will always be given an angle turned by the cam during outstroke, the dwell, angle turned by the cam during return stroke, and dwell. So before proceeding ahead, I insist you to study to listen and to see the video by Mr. Ujjwal Rane on kinematics with microstation CH07 special cams 01. So it is only 5 to 6 minute video, but you can understand it better way that how we are going to proceed with the construction of the graph as well as how we are going to do the calculations. So I will more concentrate on calculation in this video and how to plot it, how to plot displacement, velocity and accelerations graph that is explained in this video. I will explain it simultaneously, but I insist you to please watch this video before watching my lecture. So let's start with how to plot the displacement graph when the follower moves with uniform acceleration and retardation motion. So take a graph paper first or a plain paper, then angle turn during outstroke will be given to you. It may be 60 degrees, 80 degrees, 100 degrees or something else. Similarly, angle turn during dwell will also be given, and angle turn during return stroke will also be given. It may be 60 degrees, 70 degree, 80 degree or whatever it may be. So you have to choose a proper scale and you have to plot the outstroke angle turn, the angle turn during dwell, the angle turn during return stroke, and the angle turn during the second dwell part. So you have to choose a suitable scale. For example, angle turn during outstroke is suppose 90 degrees, dwell is suppose 30 degrees, angle turn during return stroke may be 100 degrees. So you have to choose a suitable scale. So you have to plot the angle turn on the x-axis over here. So first is outstroke, then dwell, then return stroke. So you have to divide this in 6 parts. First, divide angle turn during outstroke in 6 parts. Keep dwell as it is. Then divide angle turn during return stroke in 6 parts. So whatever is the angle, you have to divide it in 6 parts. If it is 60 degrees, then take 10 degrees as around 1 centimeter and make the diagram as for 6 centimeters. If it is 90 degrees, then take the angle turn as 50, take each, plot it as 6 centimeter only, and for each graduation you have to take around 15 degrees. So you have to choose a suitable scale and plot the angle turned by the cam during outstroke. So outstroke, dwell and return stroke. So total angle turned by the cam has to be plotted on the x-axis. So mainly you have to plot outstroke, dwell and return stroke. If any part is in the dwell too, so you can represent it as double arrow. So you need not to plot it completely. Now the displacement of the follower during the rotation of the cam will be given. So plot it in on y-axis over here. So suppose it is 40 mm or 50 mm. So draw a line that is equivalent to the displacement of the follower. It may be 40 mm or 50 mm or 60 mm, whatever it may be. So you have to choose a different scale for the y-axis and you have to choose a different x scale for x-axis, because On x-axis we are plotting angle turn, on y-axis we are plotting displacement. As both are different terms, so you have to choose different scales for both. So during out stroke this much angle is turned, so draw the displacement over here and complete the box over here. So here is 40 mm suppose, so this is also 40 mm and complete this box. Similarly during the dual keep it as it is, and during the return stroke again the displacement, whatever is the displacement of the follower during out stroke, the same will be the displacement of the follower during the return stroke. So draw a line of suppose 40 mm over here, draw the line of 40 mm over here and complete the box. So from start to the end just complete this box and draw the lines at the end of the out stroke and at the start of the return stroke. Now draw a vertical line passing from the center of this graduation. So if you are divided it in 6 parts, then draw a vertical line from the half of this, means at the point number 3. So draw a vertical line over here. Similarly during the return stroke draw a vertical line over here, and again in how many number of parts you have divided on the x-axis, in the same number of part you have to divide on the y-axis. So if you are divided in 6 parts, divide this vertical line in 6 parts. If you are divided it in 8 parts, you have to divide this vertical line in 8 parts. Now at each division you have to plot a vertical line equivalent to the length of the distance traveled by the follower during out stroke. So whatever is it is 40 mm. So draw 40 mm vertical lines from each division over here. So you can observe here during out stroke as well as during return stroke you have to divide it in same number of parts. So if it is 6 parts, you have to draw 6 vertical lines over here and divide this middle line also in 6 parts. The numbering you can choose whether it is 0, 1, 2, 3, 4 from bottom to up or from up to down, or you may write it as A, B, C, D or something like that. Now join from 0 to 1 on this line, join 0 to 2 on this line, join 0 to 3 on this line. Now you have to reach up to the midpoint of this vertical central line. So once you reach this point, now you have to leave this half part and you have to move in the next half part. So join 3 with this end point, join 4 with this end point and join 5 with this end point. Similarly during the return stroke, from this point, starting from this point, join 5, then join 4, then join 3. Once you reach the center point, now you have to choose the other half part. So join 3 with 0 over here, join 0 with 2, join 0 with 1 and so on. Now you had got different points over here. So you have to choose the intersection between this first line and this first line you have drawn. So the intersection we are getting over here. Similarly when you join 0 with 2 over here, so wherever it cuts the second line, so you have to mark this as a second point. Similarly the third line is this and this is your third line, so wherever there is intersection, mark this or highlight that point. Similarly highlight different points over here, over here. Similarly during the return stroke, join your first line wherever it cuts the first line over here, so mark that point or highlight that point. Similarly your second line wherever it cuts the second vertical line, so mark that point and so on. So third point, fourth point, fifth point and sixth point. So we had highlighted different points. Now with the help of a smooth curve, join all these points sequentially. So from starting from 0, first point, second point, third point, fourth, fifth and sixth. Now in the dual part there is no motion of the follower. Then during the return phase, this join like this from start of the return stroke to first point, second point, third point, fourth point, fifth point, and sixth point. We can name all these intersecting point as A, B, C, D, and so on up to M. So nomenclature you can choose as per your convenience. Now this curve, this should be a smooth freehand curve. This curve represents the displacement of the follower when the cam moves with uniform acceleration and retardation motion. So during out stroke, from the start of the out stroke, the follower moves like this. It reaches up to the midpoint of the out stroke and it moves along this curve and it reaches at the end of the out stroke. During the dwell part, the follower does not move even though the cam is rotating with the angle turn during the dwell. It may be 30 degrees, 40 degrees, or whatever it may be. Now whenever the return stroke starts, so again the follower follows this path. The displacement of the follower is represented like this. So it traces this path G, H, I, J, K, L, and M. So from the start of the out stroke, dwell, and return stroke. So this is how we can plot the displacement graph over here. Now next part is velocity of the particle moving with uniform acceleration and retardation motion. So velocity of the particle, while the particle moves with uniform acceleration and retardation motion, whether it is a particle or whether it is the follower, it is represented by V equal to 4s omega upon theta O square into theta, where V is the velocity of the follower, S is the displacement of the follower, that is the maximum displacement of the follower, omega is the angular velocity of the cam, theta O is the angle turned by the cam during out stroke, this is constant, and theta is a variable angle turned. So at any position you can take corresponding theta. While the angle turn during out stroke may be 60 degrees, so you can take theta as 10 degrees, 20 degrees. So this theta is a variable angle. So you can choose any angle during out stroke over here. Now it is represented like this. So at the start of the out stroke, the angle turned by the cam is 0. So you need to put angle turned by the cam is 0, that is theta equal to 0. So if you put theta equal to 0, keeping all these as constant, as displacement of the follower is constant, angular velocity is constant, and angle turned by the cam during out stroke is also constant. So theta is a variable over here. So at the start of the out stroke, when cam does not move, means it does not rotate, so angle turn is 0. So while you put it 0, you will get the velocity of the follower when the cam is moving with uniform acceleration and retardation motion at the start of the out stroke is 0. So you can find it as 0. You put it over here 0 and the entire equation will become 0. Now at the half of the out stroke, so at half of the out stroke, theta is half of the out stroke, so it will be theta O by 2. Theta O means angle turn during out stroke. So at half of out stroke, it will be theta O by 2. So theta O by 2, if you will put over here, so theta and theta square, its square part will get cancelled, and the equation we will get is 2s omega upon theta O. So we had put theta as theta O by 2. Theta O and square part is cancelled. 2 cancels with 4. So what will remain is 2s omega upon theta O. So at the point of half of out stroke, the velocity will be 2s omega upon theta O. Now at the end of the out stroke, even though you can put over here as theta O, so we will get 4s omega upon theta O, but at the end of out stroke, we already know that at the end of out stroke there is the start of dwell part. That means at the start of the dwell phase, the velocity is 0, means at the end of out stroke velocity must be 0, even though from the equation we put if value of theta as theta O, we will get the value of velocity, but we know that this velocity of the follower at the end of out stroke should be 0. So instead of putting the value of theta O over here, we have to directly put the velocity at the end of out stroke as 0 instead of putting in the formula. So you need to remember this part. Instead of at the end of the outstroke, velocity must be 0. Now velocity during return of the follower, as we had seen velocity during the outstroke of the follower. So velocity during return of the follower at the start of return stroke, as we had seen at the start of outstroke velocity was 0. So similarly at the start of the return stroke velocity will be 0. At the half of the return stroke, so instead of theta we have to put theta r by 2 over here. In the same formula we had used this formula over here, so we have to use the same formula over there for the return stroke. Only difference is that instead of theta o stands for outstroke, we have to put r, so it will be theta r stands for return stroke. So the formula will remain same, only difference will be theta r square over here. 4s omega upon theta r square into theta is again variable. So at the start again we will get the velocity as 0. At the end of the return stroke we will get the velocity as 0. Only velocity we are waiting some value is at the half of return stroke, and that value will again be similar to this value. Only difference is the formula will be the same. Only difference is that instead of theta o there will be theta r. So angle turn during return stroke is theta r. As we know the velocity is a vector term, so during rise if we are taking velocity as positive, so during return we must take it as negative, because velocity is a vector quantity. It indicates magnitude as well as direction. So from this formula we will get only the magnitude. To show the direction we have to put the sign as positive or negative. So in this return part you can observe here the velocity at the start of return stroke it will be 0. At the end of the return stroke again it will be 0, but at the center it will be having the similar value 4s omega upon theta r square into theta r by 2, and here that is the minus sign. So minus sign indicates that the velocity of the follower is different, the direction is reverse, means it is return phase. So we will get minus 2s omega upon theta r. So minus sign indicates the direction and theta r indicates the angle turn during return stroke. At the end of the return stroke the velocity must be 0. So we have to plot it like this. At this is the angle turn phase, or on the x-axis we have to choose the angle turn during outstroke, during dwell, and during return stroke. So what I have to do, I have to just project from the displacement diagram over here. From the displacement diagram at the start of the outstroke, at the middle of the outstroke, at the end of the outstroke. Similarly at the start of the return stroke, at the middle of the return stroke, and at the end of the return stroke. So these 6 projections we have to project in downward direction from the displacement graph. So we have to plot the velocity. Now start is 0, in the middle it is 2s omega upon theta, at the end of the outer stroke it is 0, at the start of the return stroke it is 0, at the end of the return stroke again it is 0, and at the middle of the return stroke it is 2s omega upon theta r, but its sign is minus, means we have to represent it in downward direction. Now how to plot it? As we know that it is uniform acceleration and retardation motion. The name itself indicates the acceleration is uniform or the acceleration is constant. If acceleration is constant, then rate of rise of the velocity or rate of fall of the velocity will also be constant. Means velocity is varying uniformly. As velocity is varying uniformly, so we have to represent it as a straight inclined line. So as due to uniform acceleration or constant acceleration, velocity is rising uniformly. That's why we have to represent it along the straight line. So during first half of the outstroke, the velocity is rising continuously. During second half of the outstroke, the velocity is reducing consistently. So from 0 till the middle stroke the velocity is continuously rising. From the mid of the outstroke till the end of the outstroke the velocity is reducing continuously. Similarly during the return part, as it is constant acceleration and retardation motion, so again we have to represent it along with by a straight inclined line. So from the start of the return stroke, velocity is 0. At the middle of the return stroke, the velocity is there, but it is in its direction is reverse. That's why we are showing is a negative. So we have to plot it in downward direction. So it is constant deceleration, and from the middle of the return stroke till the end of the return stroke, the velocity is continuously rising till 0. So uniform in the uniform acceleration and retardation motion, the velocity graph will be straight inclined lines. Here you can observe here, so it will be straight inclined lines. The next part is acceleration. Acceleration of the particle moving with uniform acceleration and retardation motion. So during rise of the follower or during outstroke, as we had seen, the acceleration is constant. So acceleration is rate of change of velocity with respect to time, or acceleration is slope of the velocity graph. So 4s omega upon theta o square, and in that equation only theta was the variable, so d theta upon dt, as rate of change of angular displacement with respect to time is nothing but the angular velocity. So 4s omega upon theta o square into d theta by dt is nothing but omega over here, so angular velocity will get. So the final acceleration will get is 4s omega square upon theta o square. So if we differentiate the velocity equation, we will get the acceleration equation, and it is the acceleration equation. You can observe here 4 is a constant, s is the displacement of the follower, that is again a constant, omega is angular velocity of the camshaft, again it is a constant, then angle turn during outstroke, it is again a constant. As all the terms in this equation are constant, so acceleration is also a constant. As acceleration is not a function of theta, it is not a variable, it is a constant. So acceleration will be constant from start till the end, but you can observe here we had put a plus or minus sign. So why we had put plus or minus sign, I will show you while we are plotting the graph. So during return of the follower, the acceleration will be same, only difference will be instead of theta o, we will be having theta r, and from positive negative sign we have negative to positive sign, so minus plus over here. Now how to plot it, so we will see here in the next graph. So from the start of the outstroke, you can observe here the velocity is continuously rising. As velocity is continuously rising from this graph, so its slope is positive. Slope, its equation is y2 minus y1 divided by x2 minus x1. As slope is positive from the start till the middle of our stroke, that means there is constant positive acceleration. So during the first half of outstroke, the acceleration is positive. So during first half of outstroke, again we had taken the projections from the velocity graph over here, from the at the start, at the middle, at the end of outstroke, at the start, at the middle, and at the end of return stroke. So during first half of outstroke, the velocity is rising, that's why during first half acceleration is positive. Now during second half of the velocity, we can observe here that velocity is continuously reducing till the end, or it is continuously reducing up to 0. So as its slope is negative, y2 minus y1 divided by x2 minus x1, if you calculate, you will get some negative value. As the as slope is negative, that means acceleration is negative during the second half of outstroke. As acceleration is negative, that is also called as retardation. So we have to plot it in the lower side or in the negative direction. Similarly, you can observe here at the start of the return stroke till the half of the return stroke, you can plot the slope over here. So here slope is negative. As slope is negative, that means the acceleration is negative during the first half of return stroke. Similarly, in the second half of the return stroke, if you calculate the slope, then the velocity is continuously rising from the middle of the return stroke till the end of the return stroke. That's why the slope is positive. As slope is positive, so the acceleration will also be positive in the second half of the return stroke. That's why we have to plot it as positive sign. Here it is positive, so in the upper part it is positive, acceleration is positive. Here acceleration is negative, or it is retardation or deceleration, so here we have to plot it as negative. Here it is deceleration or slope is negative, that's why we have to plot in the downward side of the x-axis. Similarly, here it is positive, that's why we have to plot on the upper side of the x-axis. So we had plotted it, that is, as the acceleration is constant, as it is acceleration is constant or slope is constant over here, so acceleration is constant and a constant is represented by a straight horizontal line over here. So during first half of outer stroke, acceleration is positive. During second half of outer stroke, the acceleration is negative. So from the start we are getting the constant acceleration from 0 to half of outer stroke, and during the second half we are getting constant retardation. Similarly over here, we are at the first half of the return stroke, we are getting constant retardation. So as it is constant, we have to represent it by a straight horizontal line, and then there is constant acceleration, so we have to represent it by a straight horizontal line, and it is positive. We already know that rate of change of displacement with respect to time is velocity. Rate of change of velocity with respect to time is nothing but acceleration. Now, rate of change of acceleration with respect to time is called as jerk. So next part is jerk. Jerk is rate of change of acceleration with respect to time, or it is we can get it by differentiating the acceleration equation with respect to time. So acceleration equation, we have 4s omega upon theta o square. You can observe here all the factors in this equation are constant, and differentiation of a constant value is always 0. So the jerk we will get from this equation is 0. So theoretically we have 0 jerk, means rate of change of acceleration with respect to time is 0. That's why the jerk in this mechanism should be 0 theoretically. But in actual practice, if you observe the graph over here, you can observe here that at the start of the outstroke, when there is no acceleration, no velocity, no displacement, and suddenly we are having a certain constant acceleration over here. So at the within no time, from at the 0 time, within no approximately 0 time, we are getting a constant acceleration of 4s omega square upon theta o square. As it is a vertical line, means from 0 to certain constant value of acceleration, it reaches to constant value of acceleration within no time, and we have to plot it as vertical line. As it is a vertical line, its slope is infinity. Slope of a vertical line is always infinity. That means within no time, from 0 acceleration to certain amount of constant acceleration we are reaching. That means infinite amount of jerk is required to achieve this. So as the acceleration is rising over here, you can observe here it is above the x-axis, the line is rising above the x-axis. That's why infinite amount of jerk is required to achieve this constant amount of acceleration at the start of outstroke. So infinite jerk is required at the outstroke. Similarly, at the middle of the outstroke, you can observe here there is certain amount of constant acceleration, and suddenly within no time we are getting constant amount of deceleration. So from positive acceleration to negative acceleration or retardation, Suddenly the acceleration is changing within no time, as it is a vertical line and slope of vertical line is infinity and slope of acceleration graph is jerk. So slope of acceleration graph is jerk and it is a vertical line. That's why we need infinite amount of jerk in the negative direction to achieve the constant amount of acceleration to constant amount of retardation value. That's why we have to plot it like this. So practically we need infinite amount of jerk to achieve this. In between start to the middle of outstroke, as it is a horizontal line, so as horizontal line have zero slope, that's why we don't have any jerk in between start of the outstroke till the middle of the outstroke, but infinite amount of jerk at the start of the outstroke, in the middle of the outstroke. Similarly at the end of the outstroke there is constant amount of retardation present whose magnitude is minus 4s omega square upon theta o square. So at the end of the outstroke, and suddenly it reaches a zero value. As it is suddenly reaches a zero value, which is represented by a straight vertical line over here, so acceleration is from certain amount of negative value reaches its zero value within no time, as it is a vertical line and slope of vertical line is infinity. Similarly slope of acceleration graph is jerk. That's why as we are getting a slope as infinite over here, so at the end of the return stroke outstroke we are getting infinite we require infinite amount of jerk to achieve zero acceleration from a negative acceleration or retardation. Now in between middle of the outstroke till the end of the outstroke, here you can observe there is a straight horizontal line, that means retardation is constant. As retardation is constant, it doesn't have any slope. As it doesn't have any slope, that means jerk is zero in between, but at the start, in the middle and at the end we have infinite amount of jerk. Similarly over here we are seeing a vertical line over here, that means infinite slope is present at the start of the return stroke. As infinite slope is present means infinite amount of jerk is required at the start of the return stroke, that is when the follower is stationary, suddenly its retardation reaches a constant value of minus 4s omega square upon theta r square, and from within no time, as it is reaches this constant value within no time, that's why infinite amount of jerk is required to achieve this. So infinite jerk we have to show in this direction, as its slope is infinity in downward direction. Similarly at the middle of the return stroke we have negative constant acceleration to positive constant acceleration within no time, so it is represented by a vertical line over here. As it is represented by vertical line and slope of vertical line is infinity and slope of acceleration graph is jerk, that's why we have to represent it by infinite arrow showing in the upward direction, as it is from negative value to positive value. So infinite positive jerk is required in the upward direction. Similarly at the end of the return stroke, you can observe here there is again a vertical line, that means its slope is again infinity and it is in the downward direction, so its slope or its jerk is negative infinite value in downward direction. So the entire graph, this is the displacement graph, you can observe here, we had seen it. So displacement versus theta graph over here, then velocity versus theta graph over here, acceleration versus theta graph over here. So in some books it is represented as displacement versus omega t, velocity versus omega t, acceleration versus omega t, and jerk versus omega t. So whether it is omega t or time or theta, we have the same graph. Only on the x-axis we can have different notations or different units, whether it is theta or omega t or time. So this is the complete graph of displacement versus time or displacement versus theta, velocity versus theta, acceleration versus theta and jerk versus theta graphs. I hope you understood. Thank you all of you.